So in this video, I want to just look at a selected bunch of examples from Pinter's Chapter 27, Problem Section A. This is a relatively long section, and so my hope is to just show a bunch, kind of just picked somewhat willy-nilly, that shows kind of how you go about thinking about these problems. So the first one I'll do is Problem 1, subproblem C, which deals with 2 plus 3i. I'm realizing if you don't have the book in front of you, the question for all of these is to show that the given number is algebraic over Q. And this means that it satisfies a monic and irreducible polynomial over Q. So what I need to do is figure out some polynomial equation that this thing satisfies. And the simplest way to do that is to set it equal to some x and then do a little bit of rearranging to try to get one simple polynomial with only rational coefficients, since it has to be defined over Q, which this thing then satisfies. So since I'm setting 2 plus 3i equal to x, any valid algebra move that I do to this will preserve that equation. And so ultimately what I want to do is work on this using algebra until there is nothing that's not defined over Q. And the thing that's not defined over Q right now is the imaginary number I. So for example, I can write 3i equals x minus 2. And now I can square both sides of this to get minus 9. Yep, because I squared is minus 1 equals x squared minus 4x plus 4. And then lastly, I can add 9 to both and get 0 equals x squared minus 4x plus 13. Now, there's a last step of all of these, which is that we have to see that it's irreducible. It's monic because the leading coefficient is 1. That's just, of course, true. For that, for example, we know that over R, we have the quadratic formula. In particular, if b squared minus 4ac is negative, this thing doesn't have any roots. And so b squared here is 16 minus 4 times 1 because it's monic times 13. And I can just stop here because clearly 4 times 13 is more than 16. That's in fact negative. All right, let's do another one. Let's keep going. The next one I want to look at is E. And E deals with the square root of I minus the square root of 2. So it's the square root of some square roots. Technique here is very similar. We're going to start by just squaring both sides. And then I get I minus the square root of 2 equals x squared. And this looks a little better in the sense of now I've eliminated one thing that was making me not rational coefficients. I got two more things that make me have not rational coefficients. And in this situation, I don't know like a simple guaranteed way to do this. We have to just like kind of try some stuff. So I'm going to try squaring both sides again, and we're just going to see what we get. So on the right, we get x to the 4. If I square this, I get I squared is minus 1 plus 2 times the product, which is minus I square root of 2 times 2. So hold on, it's minus 2i, that thing. Plus this minus squares away, the square root of 2 squared is 2. So, you know, sometimes this can make things worse when the things that are being smashed together are unrelated to each other. But in this case, it's actually getting a little better. And let me just clean this up a little bit. So if I subtract 1 from here, I get minus 2i square root of 2 plus 1. Now, how about we put that minus 1 over here? Minus 2i square root of 2 equals x to the 4 minus 1. And now lastly, if I square both sides one last time, I can get rid of this complex imaginary and otherwise irrational stuff, where this side becomes x to the 8 minus 2x to the 4 plus 1. Here, this minus goes away. I get 4. I squared is a new minus 1, so minus 4 times the square root of 2 squared is 2. So minus 4 times 2 is minus 8. So this gets me x to the 8 minus 2x to the 4 plus 9 equals 0. And I found a polynomial. It's monic. It has not just rational, but integer coefficients. So we're making progress. I should see that this thing is irreducible. In this case, another trick avails itself to me that I notice, which I don't expect there to be a good trick like this for a degree 8 polynomial in general. But this is no ordinary degree 8 polynomial. It's a polynomial of degree 2 in x to the 4. So in other words, if this thing factors, it has to factor in such a way where this is y squared minus 2y plus 9 with y equals x to the 4. And that thing I can see, again, we get b squared is 4 minus 4 times 1 times 9 is negative. So this thing doesn't factor. And so since this thing has this extra symmetry here of being invariant under x going to x to the 4, then whatever factorization it would have would also have to share this symmetry. And this thing has no ability to factorize further. So we're happy. All right, let's do one more of this type. Let's do the one, how about g, which is the cube root of 2 plus the cube root of 4. I think you guys are getting the idea now. We're going to start by setting this equal to x. And now I have cubes, so I'm going to try to cube both sides. So we get x cubed over here. And then because of the binomial formula, which I happen to just know, the cube root of this cubed is 2 plus 3 times the cube root of 2 squared plus, times the cube root of 4. This is not going to fit. So let me try to write this in such a way so that it does fit. Let's skip over the calculation in the middle, and then you guys can check my math, and hopefully it's right. So we get the cube root of 16 plus 3 times the cube root of 32 plus 4. And I know this doesn't look better, right? This is just the kind of thing that one learns from some experience that it is better. Let's simplify. This is 6. And then since these are cube roots, we know how to simplify expressions with cube roots. This is 8 times 2. So I get 6 times the cube root of 2. And it's 8 times 4 in here. So that's 6 times the cube root of 4. And then I took that 4 and combined it. And the magic is that that expression here, I guess I should include it, is equal to 6 plus 6x equals x cubed. And so that gives us a polynomial. So we're happy about that. I guess there's a question then about why this thing is irreducible. What's the simplest proof of this that I can think of? How about the rational root test? The rational root test, right? Since this is an odd degree polynomial, if it were to factor, one of the two factors would be linear, and therefore a factor would have to have a rational root. And the deal for a rational root is that it would be of the form p over q, where q has to divide the leading coefficient. And p has to divide the constant term. But in this case, the leading coefficient is 1. So actually, the rational root test tells me that any solution has to be an integer. And in particular, it would have to divide 6. So the only choices for possible rational roots are plus or minus 1, plus or minus 2, and plus or minus 3. We can just check those. That's not so bad. So for 1, we have 1 cubed minus 6 times 1 minus 6. Clearly doesn't work, right? We don't have to do all the math, right? I can just see this is very negative. For minus 1 cubed, minus 6 of minus 1 minus 6. I wrote minus 2. Oops. Minus 1. This is minus 1 plus 6 minus 6, which is equal to minus 1, not 0. Sorry, I didn't label that attempt. Let's check 2. 2 cubed minus 6 times 2 minus 6 is 8 minus 12 minus 6. It's not 0. Let's try minus 2. Minus 2 cubed minus 6 times minus 2 times minus 6. So what is this? This is getting to be much. Minus 8 plus 12 minus 6, still not 0. Almost done. We have to check 3 and minus 3. We got 3 cubed minus 6 times 3 minus 6. 27 minus 18 minus 6. That is 9 minus 6 is 3, not 0. And then lastly, we have to check minus 3 minus 6. So we got minus 27 plus 18 minus 6. Clearly negative, not 0. So before I move on and I want to talk about a problem of a different type, I want to point out that there are lots of strategies, right? There's no rule that you have to use this strategy. This strategy even was rather specific to degree 3, right? Because degree 3 implies if you factorize, you have a linear component, a linear times a quadratic or all linears. And therefore, factoring is the same thing as having a root. And so that's not going to work for you necessarily in general. But there are lots of ways that you can go about like trying to hone your search in some capacity. And it really just boils down to like what kinds of stuff you remember. So for example, like when you're looking for specific roots in a case like this, you have things like synthetic division that can help you detect the existence of roots. There's the Descartes' rule of signs, which can help you detect like how many linear versus quadratic things there may be, like how many real versus imaginary roots there could be. You can, knowing the outcome of Descartes' rule of signs, you could try to factor it. Like if you remember your Vieta formulas, something we teach our own students, is if you have to factor a quadratic, you write like x minus a, x minus b, and then that gets you some rules, namely, right, these things at one pair have to add up, the other pair have to multiply. So if you say, okay, now I know something about what the form of a factorization looks like, I get some equations. Let me try to study those equations. You can check on those guys, see what you can see. There's one thing that I know that we haven't talked about in class, but you might be served well by Googling it and keeping it in your back pocket. It's called Eisenstein's criterion. This is just like a one-shot way to prove that a polynomial of high degree doesn't factor. Oftentimes very helpful. And then the last thing that comes out to my mind is looking at things modularly. In other words, if P of X factors purely formally, right, without any, like it happens algebraically, then it also has to work mod P for various P. And so sometimes you can rule out factorizations by like comparing different situations between different kinds of working with different finite fields. And so I don't want you to give you the impression that you have to like now do a whole bunch of homework and like go memorize all of these different tricks. When I give you problems, they will always be problems that will be like doable just with what you know, or at least what my impression is of what you know. And of course, if I get that wrong, then you should feel free to drop me a note that says I have no idea what the heck we're talking about. But the point should be that if you are encountering a problem in your life, right, beyond just this class, then you may use any of these tools, or you may like poke your nose around on the internet and see what kind of tools exist. Because even this is not like an exhaustive list. These are just like the things that I know that I've tried on different problems. All right, so I've been talking for a little while now, but I want to show one more because it highlights the subtlety about transcendental numbers, but I promise it'll be quick. This is 2b, which says to explain why the square root of pi, let's scroll down a little bit, to explain that the square root of pi is algebraic over q adjoin pi squared. And so I think this is a great problem to look at because it forces us to understand what this means. So this means that we're allowed rational numbers and rational polynomials in pi squared. So an element of this object looks something like it's a finite sum of powers where I ranges from 0 to some capital N. So they can't go forever, right? Like we're not, or I mean, yeah, they can't go forever. There's no like analysis, convergence, infinite stuff here. These are finite sums of things that look like this. So like pi squared is in here, but so is like 8 over 7 pi to the 6, right? Because it's a rational multiple of pi squared cubed. This is allowed. But we can like make it more complicated by adding in other things. But we can't do like square root of 2 pi squared because this is not rational. That guy's not allowed. But otherwise, I could make it more complicated with, 14 over 3 pi to the 8, right? Any combination of rational numbers and pi squared. So when I want to prove that this thing satisfies an algebraic equation in here, the deal is the polynomial that we're going to satisfy has to have coefficients that are either rational numbers or coming from these pi squared things. So therefore, when I set this equal to x, and I need this to land in here, I can't just say x squared is pi and I'm done. Because while that gets rid of the square root, pi is not in here. Only pi squared is in here. So therefore, I have to raise this to the 4th power. X to the 4 equals pi squared. And this thing makes this element algebraic in here. We did it. All right, well, let's stop there.